Hey guys, okay, I just wanted to go over an example of this graphing thing with you real quick. Um, it's going to have you do it kind of as a bell work thing, and I still will assign a little bell work thing, but it won't be due right away. You'll have a few days. Um, so here we have a velocity versus time graph of simple harmonic motion. So if we're trying to find our variables from this, remember we got our fat variables and also angular frequency as well. Fat omega. Actually, omega 3s are fatty acids, a type of fat. Anyways, that's not physics. That's biology, I guess. Anyways, okay, back on track. So when we're looking at this, we can still see by looking at this time axis and the one full cycle, the period is 5. And so the period is going to be the same regardless of what graph we're looking at. If we're looking at position, if we're looking at velocity, if we're looking at acceleration. The period is the time it takes to go one full cycle. So right off the bat, we can see period is 5 seconds. And from that relation, we know that frequency is 1 over the period, which is just 1 over 5, 0.2 hertz. And omega is 2 pi f, which equals 2 pi over 5 radians per second. Okay, that was all pretty easy. The only little tricky thing is when we're looking for the amplitude, okay? So when we have our position, or if we're talking about pendulum, it would look something like that. It looks like your amplitude times the trig function, some trig function. Omega, if we're doing pendulum, V would be A omega times some trig function. And alpha is a function of time, acceleration as a function of time, will look like A omega squared times some trig function. So we're looking at velocity, right? This is a velocity graph. So we have a omega here, but we just want to find the amplitude. So A omega, and it's going to be, if this was a position graph, then just this distance would be your amplitude. However, it's a velocity graph. So that distance, so this distance from there to here is actually A omega. If it would be an acceleration graph, it would be A omega squared. And so these minor ticks are at distance of 0.5. So this 0.5, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. And I'm going to erase this to clear up things a little bit. This looks like it's about, so this is 3.5 right here, this is 4, so it's about 3.75. So A omega is about 3.75. And we know omega right here is 2 pi over 5. So A equals 3.75 over omega 0.75 times 5 divided by 2 pi. And let's put that into a calculator real quick. 3.75 times 5 divided by 2 divided by pi ends up to be 2.98, which I made this graph. I set the amplitude to be equal to 3, so that's close. It's about 3. Really, this probably isn't right at 3.75. It's probably 3.8 or something like that, but we're close. Good enough. 3. Amplitude is 3. So we have all these variables now. Our period is 5 seconds. Frequency is 0.2 hertz. Omega is 2 pi over 5 radians per second. And our amplitude is 3. It's velocity, so 3 meters. So there's our variables. So that means our velocity function looks like a omega, so 3 times 2 pi over 5, which is just 6 pi over 5. Now let's look at this graph. This is a negative, so it starts at the origin, that means it's a sine, and it goes downwards. So it's a negative sine graph. So actually, negative sine, and omega is, what do we say? Yeah, 2 pi over 5, 2 pi over 5 t. That is your equation for the velocity and the equation for this graph. Just like so, our x of t would be just the amplitude 3, and it would be cosine 2 pi over 5 omega t. That's a cos omega t. And our acceleration would be 3 omega squared minus 3 omega squared sine omega t. And omega is just this over here, so you can plug that in if you want to. Anyways, we scroll down, and this is what they look like. So this kind of orange-yellow one, that's our velocity that was up there, right? The blue one is our position. It's a cosine graph, and you can tell that this is 3. So for a position, this extreme value is always going to be the amplitude. And then it goes up by a factor of omega every time. So 2 pi, so it's 2 pi over 5, which is a little greater than 1.2 or something like that. So it increases by a factor of 1.2 or something, somewhere around there. So this is a omega, and then this is our acceleration. This is a omega squared. Okay. One more thing I just want to go over. I just want to talk about a pendulum real quick. So let's say this is our equilibrium, right? There's no restoring force acting on it. Theta equals 0 degrees. And we say this is positive theta hat. This is the negative theta direction. Okay. Now, whether our graph is a sine or cosine it's kind of arbitrary because we can always throw in that phase shift. It really depends on where you say t equals 0. It depends on where you start your clock. So let's say we pulled this string out here a little bit, and we hold it, and we're going to let it go, and we're going to start the clock as we let it go. Well, this is our amplitude, right? Because that's the highest it's going to go. So if you can tell, this is positive, and it's at the amplitude. So at t equals 0, we are at the amplitude, as high as it goes, and we're going to be moving, or our velocity is going to be pointed this way, angular velocity in this case, is going to be moving negative direction because it's going to be swinging down. So our graph would look like, let's see, it would just be A cos omega t. So just sketch it out real quick. Cosine graph, it starts moving down, but it's still positive. Boom, it goes negative. This is our equilibrium point. It slows down. Looks like that. So it's just a normal cosine graph. If we started the clock at, it comes, let's say it comes down here, and we start our clock as it goes through the equilibrium, well, it would just be the graph shifted. So it'd be as time 0, it'd be going, still going negative, so the slope would still be downwards, negative, and then it would turn back positive, and then boom. Then you could just say x of t is minus, it's a negative sign, a sine omega t. So, and likewise up here, it would be negative cosine. Here, it would be positive sine. That's just something to keep in mind. When looking at a physical situation, sine or cosine, you can just throw a shift anywhere, and it's kind of arbitrary. So, homework. You guys got the assignment on Albert's due Sunday. And I'm going to throw in some easy problems, kind of bell work-like problems. And we'll have those due Wednesday. Probably kind of keep up some format like this, like Albert or something due Sunday, and then some PDF that I'll hand out due on Wednesday. And it'll be something simple. It'll be similar like this, like here's a velocity graph, give me your variables. Here's this graph, give me, and then I might do something like here's this situation, plot the graph, give me the variables, find the variables, plot the graph. It'll be something like that. Alright guys, have a good weekend. I'll probably post another video Tuesday, and we'll probably kind of get back to normal class schedule, Tuesday, Thursday, Friday kind of thing. But it's all online, so I can have this stuff due whenever I want. Haha, suckers. Okay, have fun. Hope you learned something. Be smart. You are smart. Good job. I don't know. Bye.